Hi boys and girls, this video is going to comprise the lecture for section 9.2, series and convergence on page 606. Chances are that it's also going to comprise the lecture for section 9.2 as well. We'll just see how it goes. Notice that we're now going to be talking about series. Our first section we discussed sequences, and so it's a good idea for us to see the connection between the two. If a sequence of numbers is an infinite succession of numbers that follow a pattern, such as 1, 2, 3, 4, etc. up to n, then a series is the sum of those terms, 1 plus 2 plus 3 plus 4, etc. In general, a series is an expression of the form, this is a general series now, the first term a sub 1 plus the second term a sub 2 plus the third term a sub 3 plus etc. a sub n, some general term, plus continuing on because it's an infinite series. If the series stops at some final term a sub n, then the series is finite. But if the series continues indefinitely, it's an infinite series. And we will be more interested in the infinite series for the rest of our discussion of this topic, and of course for the AP exam as well. So informally, if this is an infinite sequence, a sub n is an infinite sequence, then summation notation from n equals 1 to infinity of the general term of that sequence is an infinite series, or we would just call it a series. Occasionally it is convenient to begin the index at n equals 0 rather than n equals 1. Doesn't really matter. You're adding up an infinite number of terms, so whatever the first term is kind of is not as important as you would think. So that's the connection between series and sequences. Now let's see how we're going to deal with them and determine what's happening as n gets very large. To find the sum of an infinite series, now I want you to think about that for a moment. Sum is adding up numbers. Infinite means, well, infinite. We're going to add up an infinite number of things. Now you might think, how is that possible? Surely that's impossible. But remember, we're in calculus. We're adding up infinite things all the time. Of course, the limit is going to come to our rescue and help us do some adding up of infinite things. But once again, this comes under the category of the miraculous and impossible that calculus is able to deal with. So, considering the following sequence of partial sums. Now notice that if I have a series where I've got a sub 1 plus a sub 2 plus a sub 3 plus etc. etc., a partial sum would be adding up some of those terms. S sub 1, for example, if I was looking at my previous, let me write that down, my previous sequence, which was 1, 2, 3, 4, etc., my partial sums would be the first term. The second partial sum would be adding the first two terms, a sub 1 plus a sub 2, 1 plus 2, which is 3. The third partial sum would be adding up the first three terms of the series. In this case, that would be 1 plus 2 plus 3, which is 6. And you could keep going with partial sums, the first 4 terms, 5 terms, etc., up to an n amount of terms. Then what we do is we examine these sums as a sequence. So now if I list these numbers, 1, 3, 6, etc., now it's a sequence of partial sums, and I'm wondering, will this sequence converge or diverge? Notice the next sentence says, if this sequence of partial sums converges, the series is said to converge, and it will have a sum. If the sequence of partial sums diverges, the series is said to diverge, and it will not have a sum. Diverge, remember, means to increase without bound or decrease without bound. It's not all coming together and narrowing in on a specific number. If that is happening, if we keep adding up these partial sums and it begins to narrow in on a specific number, then it's converging. That sum is converging to that specific number, and that specific number would be the sum of the sequence, now of the series. Now notice in this case, these are not going to converge. We just got sums that are getting larger, 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 but we will see series where the sequence of partial sums does converge. And it's all about figuring out when that happens. That's what we're going to be doing. But let's look at the definition of convergent and divergent series here. For the infinite series, the nth partial sum is given by this, right? So we could say S sub 1, S sub 2, S sub 3, and then S sub n is this partial sum, adding up n amount of terms. If that sequence of partial sums converges, remember, S sub 1, S sub 2, S sub 3, you look at those numbers like 1, 3, 6, if it converges to a number, a sum, then the series converges, and that limit that it's converging to is the sum of the series. If the sequence of partial sums diverges, then the series diverges. All right, let's look at some of this in action. Because what we're going to see as we discuss infinite series is the basic question is converge or diverge. And as I said before, this is going to kind of be the focus of what we discuss for the rest of this chapter, for this final topic. We will study two basic questions involving infinite series. Does the series converge or diverge? Now, what we will discover is that there are different kinds of series. They come into categories. If you're looking at a series that falls into a category, there will be rules which will tell you if it converges or diverges. However, some series won't be categorized in that way. In that case, we have a series of tests that you can use to see if the series diverges or converges. And so we're going to learn about the types of series, and we're going to learn about the types of tests for convergence or divergence in order to answer this first question. Does the series converge or diverge? And then secondly, if it does converge, what is its sum? Now, we won't always be able to find the sum of a convergent sequence, but often we will. Notice it says that these questions are not always easy to answer, especially the second one. So we had better get started. Look at example 1 on page 607. We have this particular series, which is the sum of this general term. So in other words, here is our sequence, 1/2, 1/4, 1/8. If we were just looking at the terms as a sequence, the general term would be 1 over 2 to the n. So summing up that general term from 1 to infinity is going to be, of course, our sequence. Now, our series. Sorry, I keep saying the wrong word. It's kind of confusing. So let's look at some partial sums. S sub 1 is, of course, the first term only, 1/2. S sub 2 is going to be adding up the first two terms, 1/2 plus 1/4, which is 3/4. Then S sub 3 is going to be 1/2 plus 1/4 plus 1/8. When you add that up, you get 7/8. Now, let's examine these partial sums as a sequence. I'll use a different color to show you what it looks like. If I was looking at this sequence, 1/2, 3/4, 7/8, and wondering if this is going to converge, I might want to find the general term of this sequence of partial sums. It's not the same as the general term of these terms. It's now we're looking at the partial sums to get a general term for that. Well, notice that the denominators are even numbers. We learned, of course, that that can be easily represented by just 2n. The numerators are one less, in each case, one less than the denominator. So the even number -1 gives us the numerator. So this is the general term of the sequence of partial sums. So we could say then S sub n is going to be 1/2, 3/4, 7/8. The general term then is 2n minus 1 over 2n. Now, we can use this general term to see if the sequence of partial sums converges, just like we were finding out if the general term of an ordinary sequence would converge. Now that we're summing things up and looking at that as a sequence, we can once again take the limit as n approaches infinity of 2n minus 1 over 2n to see if this general term of this sequence converges. Now I'm going to rewrite this. Since this is a monomial expression, I can rewrite this as 1 minus 1 over 2n. And when I plug infinity in for n, this becomes 1 minus 1 over infinity, which as we know is 1 minus 0, which is 1. Therefore, the sequence of partial sums converges to 1, and therefore 1 is the sum of this series. If I added all of these numbers up to infinity, I would get 1. And the way I figured that out was doing little bits of adding at a time. 1/2, 1/2 plus 1/4, 1/2 plus 1/4 plus 1/8. And as I was looking at what these sums were becoming and what they looked like in general, then I could assume that if I had all of them added up, I can figure out what the sum is going to be. And that's what we do. Now, let's look at another example of a particular series. This is the same example actually on page 607. It's just the second part, letter B or something like that. Now once again, let's look at some partial sums. This is the general term of the sequence. Here's a sub 1, a sub 2, a sub 3, a sub n. Now as we start adding up those terms, let's see what happens. The partial sum, s sub 1, is going to be 1 minus 1/2, which of course is just 1/2. Now look at the second partial sum. Remember, this is a term and then this is a term. So the second partial sum will be adding up these two. It's going to be 1 minus 1/2, and I'm just going to go ahead and not put the parentheses, plus 1/2 minus 1/3. This, because these two middle ones cancel out, this becomes 1 minus 1/3, which is 2/3. Now let's add up or look at the third partial sum. And if this is the third term, then that means let's add up these three to get this partial sum. We have 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. Again, notice these pairs of terms on the inside that cancel, giving you 1 minus 1/4, which is 3/4. Now, as we look at these numbers, we can see that in each case, what ends up happening, since the inside pairs are canceling out, we end up with the first number of the first term and the second number of the last term. So essentially what we end up with for our general term here is, I think we call it n. Wait, do we call it n? Or do we call it 1? I guess we'll just call it 1, since in this case it is 1. And then minus this term right here, which is the second piece of each term, 1 over n plus 1. This describes the general term. For example, when it was 1, we had 1 minus 1/2. When it was 2, we had 1 minus 1/3. When it was 3, we had 1 minus 1/4, and we can extrapolate that out to being 1 minus the nth term, which is 1 over n plus 1. So, if this is our general term, let's discover if this series converges or diverges by taking the limit as n approaches infinity of 1 minus 1 over n plus 1. Now you can already see what's going to happen when I plug infinity into this denominator. I end up with 1 minus 1 over infinity, 1 minus 0, which is 1. So once again, the series converges to 1, and the sum, therefore the sum of this series is 1. If I added all of these terms up to infinity, the answer would ultimately be 1, which is pretty amazing. We're pretty amazing, boys and girls, and we're able to do this. Now let's look at this guy. You might already be able to look at this guy and see that chances are it's not going to converge. Because look what happens when we start adding up partial sums. We get s of 1 is 1. We get s sub 2 is 1 plus 1, which is 2. We get s sub 3, which is 1 plus 1 plus 1, which is 3. If we look now at these partial sums as a sequence, 1, 2, 3, dot, 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 the general term is going to be n. This is not approaching any particular number or limit. In fact, if we really wanted to go so far and say is what then is the limit as n approaches infinity of n, well, it's infinity. Obviously, it's increasing without bound. Therefore, this series diverges. Okay, 15 minutes and we're only on example 1. This might be more than one video, boys and girls. Now, let's take a closer look at example 1b. This is a certain kind of series, and it's the first one that we're going to discuss where the terms fall into a category. This category is called telescoping series, and you might kind of understand why it's called telescoping series. We saw that it was when it was all spread out, it looked one way, but as we started canceling terms that were opposites of each other in sign, it sort of detelescoped into a shorter series, and that's why it's called a telescoping series. It turns out that inner terms cancel each other out. Here's a general look at what a telescoping series looks like. B sub 1 minus B sub 2 plus B sub 2 minus B sub 3 plus B sub 3 minus B sub 4. Note that B sub 2 is canceled out by the second term here. B sub 3 is canceled out by the third term here, etc. The nth partial term is the first guy and the last guy. And again, it's the general term, whatever the n sub 1, b n sub n plus 1 term is sub n plus 1 term. That is what the general term of this series is. Because that's the nth partial term, it follows that a telescoping series will converge if and only if this approaches a certain number. So if it does approach a finite number, then it converges. And its sum will be b sub 1, that number, remember in the previous example it was 1, minus the limit as it approaches infinity of the b sub n plus 1 term. Let's look at an example to see how this is going to work. And it's going to bring up our old friend partial fractions, because this doesn't look like a telescoping series. We're looking for a telescoping series as something like b2 minus b3 or something like that. This is just one term, but look what happens when we separate this into 2n minus 1, 2n plus 1 as our denominator. We know that we can rewrite this as two separate rational expressions by making this a over 2n minus 1 and then plus b over 2n plus 1. Now again, using our technique of discovering what a and b are, a would need to be multiplied by 2n plus 1, so I'll just distribute that. 2an plus a plus b would need to be multiplied by 2n minus 1, so I'll distribute that. 2bn minus b equals this numerator 2. So we have these two equations we can put together. 2an plus 2bn, and since there's no n term on the right side of that equation, that's going to equal 0. Or actually, I should have just written that as 2a plus 2b, not with the n's, equals 0. And then the other equation that we have is a minus b is equal to 2. So let's multiply the second equation by 2, rewrite it. 2a minus 2b is equal to 4, and when I add these two equations together, I get 4a equals 4, which means a is equal to 1, and then since 1 minus b equals 2, we end up with negative b is equal to 1, b is equal to negative 1. Now, let's rewrite this series. The sum, as n goes from 1 to infinity of a is equal to 1, so we're going to have 1 over 2n minus 1 plus, or actually since it's a negative 1 there, we'll go ahead and write minus 1 over 2n plus 1. Now it is a telescoping series, so exciting. Now because we know that this is a telescoping series, we can do certain things with it. Let's find some partial sums first of all. S sub 1 is going to be 1 over 2 times 1 minus 1, which is 1, minus 2 times 1 plus 1 is going to be 1/3. So that's our first partial sum, 1 minus 1/3, which is 2/3. Now let's look at your second partial sum. We're going to have 1 over 1 minus 1/3, that was the first term. And then when we put plus, now we're going to add the second term, which is now 1 over 2 times 2 minus 1, which is 1/3. And then 1 over 2 times 2 plus 1, which is minus 1/5. Sorry, I keep forgetting that minus for some reason. But boys and girls, look what happens. These guys cancel because it's a telescoping series. 1 minus 1/5 is 4/5. Let's look at the third partial term just for fun. It's the first one, might as well write that as 1 now, plus the second one, plus the third one, which we get from putting 3 in for n. 6 minus 1 is 1/5. And then putting 3 in here, 6 plus 1, 1/7, minus 1/7. Again, telescoping series, all of these inner terms cancel out, and we end up with 1 minus 1/7, which is 6/7. Now we know that the general term here is going to be 1, the partial sum, the general term for the partial sum is going to be 1, our first term there, minus 1 over 2n plus 1. The second piece of each term is all that's left. So let's see if this converges or diverges by taking the limit. The limit of, as n approaches infinity, of 1 minus 1 over 2n plus 1. Notice once again putting infinity into this denominator makes this term go to 0. So once again it's 1. That means since the limit of the nth term of the sequence of partial sums converges to 1, the sum of the series is 1. There you have it. Now let's keep going. Now we're going to talk about another type of series. We've talked about one type of series, the telescoping series, but now we're going to turn our attention to the geometric series. Once again, if a series falls into a category which can be identified, in this case a geometric series, we have some rules that we can use to determine whether or not it converges or diverges and what the sum is. So let's examine the series from example 1a a bit more closely. This is an example of a geometric series of the form a, some constant, times r to the n. And notice that the r is a factor that's increasing by powers as you continue out the series. A can't be 0, and there's a ratio r that's being multiplied each time by each term. If you look at this particular series as we discussed before, 1/2 is r, I'm sorry, 1/2 is a, and then r is going to be 1/2 to the n power. Now the reason why this works is because look at the first term, it's 1/2. But in this general form, n starts with 0. So if n is 0 for the first term, then of course 1/2 to the 0 power is 1. 1 times 1/2 gives us 1/2. When n is 2, then of course that's 1/4. When n is 1, sorry, it's 1/2 times 1, okay, when you get the idea. So when n is 0, it becomes 1/2. When n is 1, it becomes 1/4. When n is 2, it becomes 1/8. Eventually, I thought I would get there. But the idea here is that this is A and this is R. Now, they're not always the same number, but they just happen to be in this particular geometric series. The reason why it's important to identify A and R is because look at this theorem. A geometric series with ratio R diverges if the absolute value of that ratio is greater than or equal to 1. Greater than or equal to 1. However, if the absolute value of that ratio, so this could be a positive or negative 1/2, if it's between 0 and 1, then the series converges. Not only that, but to the sum A over 1 minus R. So if you recognize that a series is geometric, identify what A and R are. If R is between 0 and 1, it converges, and the sum is A over 1 minus R. So we can see in our case that the R for this particular series is between 0 and 1, so we know that this converges. Of course, we already knew that because we already did this example. Remember, there's more than one way to determine convergence, but now we're looking at this as a geometric series. Now, let's see what the sum is. The sum is going to be A 1/2 over 1 minus R, which is 1 minus 1/2. This is 1/2 over 1/2, which is 1. Therefore, the sum of this infinite series is 1. Now, this just confirms the result that we got when we did example 1. Now let's do a couple more examples, convergent and divergent geometric series. First, we need to identify that this is a geometric series. And in this case, you can see that it is. Let's rewrite this so it looks like this. 3 times 1/2 to the n power. So remember, we're looking to be able to rewrite this as AR to the n power. And so 3 is A. R, our ratio in this particular case, is 1/2. So it falls within the range of convergence. Remember, it converges if R is between 0 and 1. In this case, that means it does converge. So let's find the sum. The sum is A over 1 minus R. That means 3 over 1 minus 1/2, which is 3 over 1/2, which is 6. Therefore, this sum converges to 6. The series adds up all of those infinite terms to 6. Now let's look at letter B. Once again, this comes into the category of a geometric series, A R to the n. In this case, A is 1, the number out here being multiplied by each term is 1. R is 3/2, of course, to the n. But notice in this case that since 3/2 is greater than 1, then this series diverges. That's it. There's no finding a sum since it increases without bound, and we're done with that. Now, notice that we are going to introduce, after we have determined two types of series, the telescoping series and the geometric series, and we learned some rules for determining whether or not those series converges or diverges. Now let's learn our first test for divergence, the nth term test for divergence. The following theorem states that if a series converges, the limit of its nth term must be 0. Now remember, we have found limits of nth terms before. Sometimes they're 0, sometimes they're not. But if a series converges, the limit of that nth term is 0. Okay? Now, you could have a limit of an nth term being 0 and the series not necessarily converge, but when it does converge, then definitely the limit of the nth term would be 0. Because of this fact, we can use the contrapositive of this theorem as a useful test for divergence. So notice this is the nth term test for divergence. This does not help us determine convergence, just whether or not a series diverges. The nth term test for divergence states that if the limit of the nth term of a series does not converge to 0, then the series must diverge. Once again, remember, if a series converges, we would find that that nth term has a limit of 0. So if we're looking at a series and we see that the nth term has a limit that is not 0, we know for sure that that series did not converge. It diverged. That's why this is a test for divergence. So let's see how that works in the next example. For letter A, example 5 on page 611, here is our nth term. We go straight to the nth term. We're going to see if that diverges or if that limit as n approaches infinity of this nth term. The idea is now going to be, is it equal to 0? Because if it's not equal to 0, that series cannot possibly converge. It diverges. But of course, look what happens when you put infinity in for n. This increases without bound. Essentially, you get infinity. Therefore, since this is not 0, we know that this series diverges. Now, let's look at this general term. We're going to take the limit as n approaches infinity of n factorial over 2n factorial plus 1. Now notice I have up here P.S. memorize the following, that the limit as n approaches infinity of 1 over n factorial is 0, because we're going to use a technique that we've seen before to rewrite this. Let's divide every term in this rational expression by n factorial. N factorial over n factorial over 2n factorial over n factorial plus 1 over n factorial. Just rewriting this by dividing by the factorial term gives us 1 over 2 plus 1 over n factorial. Well, remember we learned that the limit as n approaches infinity of 1 over n factorial is 0. So when we take the limit here as n approaches infinity and plug infinity in over here, we get 1/2 as the limit of the nth term of this sequence now, or this series. Now remember, what we're learning here is that if it's not 0, then the series diverges. So even though we got a limit, a number, it wasn't infinity, it was a number, because it's not 0, we know that this series diverges. One more. We have the limit as n approaches infinity of this nth term, general term, 1 over n. We know the drill. Put infinity in for n, we get 0. Now here's the deal, boys and girls. Because this is 0, then we don't know if it converges or diverges. The nth term test for divergence only tells us that the series diverges when it's not 0. So when it wasn't 0, we're like, bam, diverge. When it wasn't 0, bam, diverge. When it is 0, this test doesn't help us. It just gives us inconclusive evidence. We don't know for sure if it diverges or not. Now let me pause for a moment and see where we are. Okay, I'm back, and I want to say, since this is already a 33-minute video, I had planned on also doing section 9.2 in the same video, but good grief, that would be obscenely long, so I'm not going to do it. So I'm going to close this video off for section 9.2 and then do a separate video for section 9.3.